Voltage drop calculations in alternating current systems, whether single-phase or three-phase, primarily depend on the total length of the cable run, irrespective of how many individual runs constitute that total length. Voltage drop is a manifestation of the conductor's inherent resistance to the flow of electrical current. This resistance is directly proportional to the length of the conductor. A longer conductor presents a greater resistance, leading to a more significant voltage drop. Conversely, the number of parallel runs does not alter the total length of a conductor required for the circuit. If you consider a scenario where a circuit requires a total cable length of, for instance, 100 feet, the voltage drop will be determined by this 100-foot length, regardless of whether it's a single 100-foot run or two parallel runs of 50 feet each. The voltage drop formulas for single-phase and three-phase alternating current systems are as follows. For a single-phase alternating current system, the voltage drop, denoted as volts drop, is calculated using the formula volts drop equals 2 times I times R times L divided by 1000, where I represents the current in amps, R represents the resistance in ohms per unit length, and L represents the length of the cable in feet. For a three-phase alternating current system, the voltage drop is calculated using the formula volts drop equals 1.732 times I times R times L divided by 1000, where I represents the current in amps, R represents the resistance in ohms per unit length, and L represents the length of the cable in feet. The factor of 1.732, which is the square root of 3, accounts for the phase relationship in a three-phase system. To illustrate this principle, consider a practical example. Suppose we have a circuit requiring a 100-foot cable with a resistance of 0.1 ohms per foot, carrying a current of 10 amps in a single-phase alternating current system. If the cable is run as a single 100-foot length, the voltage drop calculation is as follows: volts drop equals 2 times 10 amps times 0.1 ohms per foot times 100 feet divided by 1000, resulting in a voltage drop of 0.2 volts. Now, consider the same circuit but with the cable run as two parallel runs of 50 feet each. The voltage drop calculation for each 50-foot run is volts drop equals 2 times 10 amps times 0.1 ohms per foot times 50 feet divided by 1000. Resulting in a voltage drop of 0.1 volts per run. However, since the total length of the cable is still 100 feet, the overall voltage drop for the circuit remains the same. Because we are using two 50-foot runs in parallel, each cable carries half the current. This means the current I in the equation is now 5 amps. So, volts drop equals 2 times 5 amps times 0.1 ohms times 50 feet divided by 1000, which equals 0.5 volts. As you can see, the voltage drop is consistent regardless of the number of runs. In essence, the crucial factor determining voltage drop is the total length of the cable required to complete the circuit. The number of parallel runs does not influence the overall voltage drop because it doesn't alter the total conductor length. Understanding this concept is essential for accurately calculating voltage drop in electrical circuits and ensuring that equipment receives the necessary voltage for proper operation. Voltage drop can lead to inefficiencies, equipment malfunction, and even safety hazards if not properly addressed. It is important to consult the National Electrical Code, or NEC, for specific guidelines and requirements related to voltage drop in electrical installations. The NEC provides recommendations for maximum voltage drop allowed in branch circuits and feeders to ensure optimal performance and prevent potential problems. Factors such as conductor size, conductor material, circuit length, and load current all play a role in determining voltage drop. Electrical engineers and electricians use these factors to select appropriate conductors and design circuits that minimize voltage drop and meet the requirements of the NEC. In addition to the NEC, other industry standards and best practices provide guidance on voltage drop calculations and mitigation techniques. These resources offer valuable information and tools for designing and installing electrical systems that are safe, reliable, and efficient. By adhering to these standards and guidelines, electrical professionals can ensure that electrical equipment operates within its specified voltage range, minimizing the risk of damage, malfunction, or reduced performance. In summary, voltage drop calculations in both single-phase and three-phase alternating current systems depend primarily on the total length of the cable run, irrespective of the number of individual runs. The number of parallel runs does not influence the overall voltage drop. Understanding this concept is crucial for accurate electrical system design and ensuring safe and efficient operation of electrical equipment. Remember to always consult relevant codes, standards, and guidelines for specific requirements and recommendations related to voltage drop in electrical installations. In practical applications, it's also crucial to consider directing factors that may affect the ampacity of conductors. Ampacity refers to the current carrying capacity of a conductor, and it's influenced by factors like ambient temperature, the number of conductors bundled together, and the type of insulation. When conductors are installed in environments with high ambient temperatures or bundled together, their ampacity decreases. This means they can carry less current without overheating. To account for these effects, directing factors are applied to the conductor's ampacity rating. These factors are typically provided in tables within the NEC or other relevant standards. For example, if a conductor has an ampacity of 30 amps at a specific temperature and a directing factor of 0.8 is applied due to high ambient temperature, the adjusted ampacity becomes 30 amps times 0.8, which equals 24 amps. This derated ampacity should be used when determining the appropriate conductor size for a particular load. Furthermore, it's essential to consider voltage drop in relation to the conductor's ampacity. While voltage drop calculations determine the voltage loss along a conductor, the conductor's ampacity ensures that it can safely carry the required current without overheating or causing damage. Selecting a conductor with an adequate ampacity rating is crucial for preventing thermal overload and potential fire hazards. In addition to ampacity and voltage drop, other factors that influence conductor selection include the type of insulation, the environment in which the conductor will be installed, and any specific requirements of the application. Different types of insulation offer varying degrees of resistance to heat, moisture, and chemicals. The environment in which the conductor will be installed can also impact its performance and lifespan. For example, conductors installed in corrosive environments may require special coatings or insulation to prevent degradation. Considering all of these factors is essential for selecting the appropriate conductor for a given application and ensuring safe, reliable, and efficient electrical system operation. Furthermore, it is important to consider the impact of harmonics on voltage drop and conductor sizing. Harmonics are distortions of the sinusoidal waveform of alternating current that can occur due to nonlinear loads such as electronic devices, variable frequency drives, and some types of lighting. Harmonics can increase the current flowing through conductors, leading to increased voltage drop and potentially overloading the conductors. To mitigate the effects of harmonics, it may be necessary to use larger conductors or to install harmonic filters to reduce the harmonic content in the electrical system. Harmonic filters are devices that selectively block or attenuate specific harmonic frequencies, reducing their impact on the electrical system. It is also important to consider the impact of voltage drop on the performance of sensitive electronic equipment. Many electronic devices, such as computers, servers, and medical equipment, require a stable voltage supply to operate correctly. Excessive voltage drop can cause these devices to malfunction, shut down, or even be damaged. To ensure proper operation of sensitive electronic equipment, it may be necessary to use dedicated circuits with larger conductors or to install voltage regulators to maintain a stable voltage supply. Voltage regulators are devices that automatically adjust the voltage to compensate for voltage fluctuations and maintain a constant output voltage. They can be used to provide a stable voltage supply to sensitive electronic equipment, even in the presence of voltage drop or other voltage variations. In summary, accurate voltage drop calculations are essential for ensuring safe, reliable, and efficient electrical system operation. It is important to consider all relevant factors, including conductor length, conductor resistance, load current, ampacity, directing factors, harmonics, and the requirements of sensitive electronic equipment. By carefully considering these factors and following relevant codes, standards, and guidelines, electrical professionals can design and install electrical systems that minimize voltage drop and provide a stable voltage supply to all connected equipment. We remember that the National Electrical Code, or NEC, is a comprehensive set of standards for electrical installations in the United States. It is updated every 3 years to reflect the latest advancements in electrical technology and to address emerging safety concerns. The NEC provides detailed requirements for conductor sizing, overcurrent protection, grounding, wiring methods, and other aspects of electrical installations. It is essential for electrical professionals to stay up to date with the latest edition of the NEC and to follow its requirements when designing and installing electrical systems. In addition to the NEC, other organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA, develop standards and guidelines related to electrical safety and performance. These standards and guidelines provide valuable information and best practices for electrical professionals to ensure the safe and reliable operation of electrical systems. It is important to consult these resources and to stay informed about the latest developments in electrical technology and safety. Furthermore, it is crucial to conduct regular inspections and maintenance of electrical systems to identify and address any potential problems before they lead to failures or safety hazards. Regular inspections can help to detect loose connections, damaged insulation, overloaded circuits, and other issues that can contribute to voltage drop or other electrical problems. Maintenance activities such as tightening connections, replacing damaged components, and cleaning electrical equipment can help to prevent these problems and to ensure the continued safe and reliable operation of electrical systems. Finally, it is important to emphasize the importance of qualified and trained electrical professionals for designing, installing, and maintaining electrical systems. Electrical work can be dangerous, and it is essential to have the knowledge, skills, and experience necessary to perform it safely and correctly. Qualified electrical professionals have completed extensive training and have demonstrated their competence through certification or licensing. They are familiar with the NEC and other relevant standards and guidelines, and they have the expertise to design and install electrical systems that meet the requirements of these standards and that operate safely and reliably. When hiring an electrical professional, it is important to verify their credentials and to ensure that they are properly licensed and insured. It is also a good idea to ask for references and to check their reputation with previous clients. By hiring a qualified electrical professional, you can have confidence that your electrical system will be designed, installed, and maintained to the highest standards of safety and performance. In conclusion, understanding voltage drop calculations, considering ampacity inverting factors, mitigating the effects of harmonics, and ensuring proper voltage regulation are all essential for designing, installing, and maintaining safe, reliable, and efficient electrical systems. It is crucial to consult relevant codes, standards, and guidelines to conduct regular inspections and maintenance, and to hire qualified and trained electrical professionals to ensure the continued safe and reliable operation of electrical systems. Always prioritize safety when working with electricity, and never attempt to perform electrical work unless you are qualified and trained to do so. Electricity is a powerful force that can be dangerous if not handled properly. By following safe work practices and by adhering to relevant codes and standards, you can minimize the risk of electrical accidents and ensure the safety of yourself and others. Remember to always disconnect power before working on any electrical equipment, to use appropriate personal protective equipment, and to follow lockout-tagout procedures to prevent accidental energization. By taking these precautions, you can help to create a safe working environment and to prevent electrical injuries and fatalities. Electrical safety is a shared responsibility, and it is important for everyone to be aware of the potential hazards associated with electricity and to take steps to minimize these hazards. By working together, we can create a safer electrical environment for ourselves, our families, and our communities.